Let me start the second day of the conference on Shimura varieties, which is the first day on Shimura varieties, special day on that. And let me introduce speakers for this morning's session. It's my pleasure to introduce Professor Richard Taylor from Institute for Advanced Study. He will speak on reciprocity laws. Richard?
Thank you. It's a great pleasure to be able to be here and help celebrate your last house. I'm interested. What I want to do this morning is talk about another concrete project which the fundamental elements of application actually form what looks like 99% of the audience. I would ask to give a talk accessible to all mathematicians. I'm not saying that none of this. That's what I plan to do. My apologies. Those of you who know.
Is your mic on? Your microphone?
Oh, the microphone is gone, but this is not. Not doing anything. Thank you. Yeah, thank you very much. So the topic of my talk is reciprocity laws, and the general problem is to fix a polynomial equation or a bunch of polynomial equations with rational or integral coefficients, reduce them among modulo a varying prime number of p, and count the number of solutions. There will always be a finite number of solutions because there are only a finite number of integers modulo p. We had 10 variables and there are at most p to the 10 possible solutions, and we can, if you like, run through them and count how many there are. Oops. Maybe that was my problem. I was trying to go the wrong way. So the first sort of question one can ask about them is reciprocity laws. This asks for some rule that, given the prime, will return the number of solutions modulo p by some procedure that has nothing to do with the counting, with the sort of obvious counting procedure, involving some completely different sort of mathematics. And the second sort of question one can ask, which I won't emphasize in this talk, but is related, and I will mention somewhat because they fit naturally together, are density theorems. Instead of asking for a given large prime how many solutions does this system of equations have, one can ask, as one let the primes vary, what sort of statistical behavior is there? What, on average, how many solutions there are? What's the error, and so on? Well, the start of this subject was in the second half of the 18th century, when Euler and Legendre were experimenting with these questions and came across what's now called the law of quadratic reciprocity. They were unable to prove it, but at the very end of the 18th century, in 1796, Gauss was able to prove it. It was supposed to have been his favorite theorem, and he returned to it again and again during his life, gave many different proofs. And it concerns the sort of simplest non-trivial case, a quadratic equation in one variable. So we fix an integer n, and we simply ask, modulo a large prime, how many square roots does it have? And it's easy to see that it either has 0, 1, or 2 square roots, just as you see over the complex numbers. And in fact, 1 only occurs very, very rarely, so it's really a question of when it has no square root and when it has 2 square roots. And the extraordinary thing that Gauss proved was that whether n has a square root modulo p depends only on p modulo 4 times n. So if you're not familiar with this thing, maybe that doesn't seem so surprising. I mean, the congruence is in both places, but there's really absolutely no reason why congruence is modulo p, or no apparent reason why congruence is modulo p should have anything to do with congruence is modulo 4 times n. This is commonly taught to undergraduates in the first course in number theory. The proof isn't terribly sophisticated. It's sometimes a talk to advanced high school students. But nonetheless, I don't know a proof that really explains to me why this should be true. It still seems to be something of a mystery. Well, let me give an example to illustrate the effectiveness of it. So suppose I ask whether 3 has a square root modulo 2013-2011, which is a prime number. Well, according to Gauss's theorem, that will only depend on this prime 2013-2011 modulo 4 times 3, modulo 12. And if one divides 2013-2011 by 12, one gets a remainder 7. So 3 has a square root modulo 2013-2011, if and only if it has a square root modulo 7. And modulo 7, it's easy to enumerate the squares. 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 2, so the only squares are 0, 1, 2, and 4. Modulo 7, 3 isn't one of them. 3 has no square root modulo 7, so it has no square root modulo 2013-2011. Okay, well, the second sort of question I was mentioning was the sort of statistical behavior. We have this rule that now allows us very effectively to determine whether a given number has a square root modulo any prime, but if we fix a number and let the prime vary, for what fractions of primes does it have a square root, and for what fraction doesn't it have a square root? And there's a sort of obvious guess, and that's right. Dirichlet proved, about 40 years after Gauss's work, that if n is not a perfect square, of course, if it is a perfect square, it has a square root mod p for any p, namely the reduction of its square root in the integers. But if n is not a perfect square, then modulo half the primes, it has 2 square roots, and modulo the other half of the primes, it has no square roots. And Dirichet's proof of this fact was very much it definitely uses Gauss's law of quadratic reciprocity. I don't know an example where one of these distribution questions can be attacked without knowing the corresponding reciprocity law first. Maybe more than one reciprocity law. I should also say that Dirichlet gave a slightly technical definition of what it means to be half the primes, and wasn't for another 60 years that the more natural definition, that it was shown that the more natural definition could be used. At the end of the 19th century, de la Vallée-Poussin showed that the most natural way of phrasing this theorem, that if you just count the prime numbers up to t, modulo which n has no square root, and divide by all the prime numbers less than t, and let t go to infinity, this tends to a half. And similarly, if you count the fraction of primes up to t for which n does have a square root and let t goes to infinity, that also tends to 1/2. Well, Langlands has conjectured so the natural question of, does this generalize beyond quadratic equations? And there was an enormous industry throughout the 19th century and the first half of the 20th century, which generalized it to particular sorts of polynomial equations. I can come back to this a bit later, the ones with abelian Galois group, called class field theory, one of the great achievements of the early part of the last century. But until the 1950s, I think there was no real suspicion that anything more general might be true. We now believe that there are completely general reciprocity laws. As I say, in the 1970s, Langlands proposed a reciprocity law that would apply to any polynomial with rational coefficients, but it's very far from being known. We still don't even know it for the general quintic equation. And I'll come back to this. On the other hand, Frobenius, in 1880, found a density theorem that was valid for any one-variable polynomial equation. And partly because I very much like Frobenius' theorem, and partly because it gives me an excuse to introduce Galois theory, I'm going to spend a little while talking about Frobenius' theorem, and I'm going to do it in this particular context. As I say, it's completely general, but I think the ideas are clear in a concrete example. I'm going to look at the polynomial x to the fourth minus 2. So as I say, to discuss Frobenius' density theorem, I have to tell you a little bit about Galois theory. So Galois told us that if you're studying an equation in one variable, the thing to do is to look at the permutations of the roots that preserve the algebraic structure. More precisely, preserve the algebraic structure means preserve any polynomial relations between the roots with rational coefficients. So this polynomial has 4 roots. It has the real fourth root of 2. I suppose if I'm clever, I can point to the real fourth root of 2. It's negative, I times it, and minus I times it. And there is here an obvious relation. If I take the real fourth root of 2 and add it to the real positive fourth root of 2 and add it to the real negative fourth root of 2, I get 0. So I'm only going to consider permutations of these 4 roots, so a subgroup of the symmetric group on 4 letters, which preserves relations like this. And in this case, this is the only relation you need to worry about. So if one looks at this, or maybe plot the roots, what we're saying, we have to consider permutations of these 4 complex numbers, which preserve the fact that these 2 are diagonally opposite each other, and preserve the fact that these 2 are diagonally opposite each other. And in this case, the only permutations are the symmetries of the square. It's easy to check. Reflection in the 2 axes, reflection in the 2 diagonals, and rotations. I gave a talk a bit like this in front of some physicists who came away from this with the idea that all elements of Galois groups preserve distance in the complex plane. They happen to in this example, but that's not a general phenomenon. You don't want to think, usually these Galois symmetries behave very badly with respect to the metrics, but just a coincidence in this case that they look like geometric symmetries. So as I say, the symmetry of the square is a dihedral group of order 8. I've listed the permutations here of the roots you find. The identity, there's 2 4 cycles, there's a pair of transpositions, complex conjugation comes in here, transposition that keeps the imaginary roots the same and flips the other 2, and then 3 products of 2 transpositions. And what Frobenius proved in 1880 was that for any one-variable polynomial f, the fraction of primes modulo which it has r solutions is exactly equal to the fraction of elements of the Galois group which fix r roots of the equation. So if we go back to this example, there's one element that fixes all 4 roots. There are 2 elements, these 2 transpositions, that fix 2 roots, and there are 5 elements which fix none of the roots. So according to Frobenius's law, modulo 5/8 of the prime, 2 has no 4th root. Modulo 2/8, or a quarter of the prime, 2 has exactly 2 4th roots, and modulo 1/8 of the primes, 2 has 4 4th roots, which I've written here. And I don't think, if you didn't know about Frobenius's law, I don't think you would have guessed this. In the case of the quadratic equation in one variable, you might well have guessed that these were the modulo half the primes it has a 4th root, and modulo half square root, and modulo half the primes it doesn't. I don't think you'd have guessed that modulo 5/8 of the prime it has no 4th root, for instance. I like to, when I give talks like this, ask the audience to guess ahead of time, but there seem to be too many number theorists in this audience to try doing that here. And in fact, 40 years after Frobenius's work, there's a much stronger version of the same theorem was proved. It really sort of points the way to the future of the subject, so I want to discuss that, Chebotarev's density theorem. It turns out that in the Galois group of any one variable polynomial, there are a series of special elements, or strictly speaking, conjugacy classes, indexed by the prime numbers. So for each, or at least all but finitely many prime numbers p, there's a special element of the Galois group, the Frobenius element. And it has, in particular, the property that the number of roots of f modulo p is exactly equal to the number of roots of x fixed by this special element of the Galois group. That's what we were talking about just a moment ago, this relationship between the number of roots of f mod p and the number of roots fixed by some element of the Galois group. So there's these special elements of the Galois group, or strictly speaking, conjugacy classes. And Frobenius' theorem, before I come to Chebotarev's theorem, but before I come to that, let me do an example. So I'm again going to consider the polynomial x to the fourth minus 2, and I'm going to try and find the Frobenius element at 7. If I try and solve this equation modulo 7, I find that there are I can find two fourth roots of 2 modulo 7, namely 2 and minus 2. If you look at 2 to the fourth is 16, which is 2 mod 7. So we have these two roots, and then if I factorize this polynomial modulo 7, there's also a irreducible quadratic factor. So the Frobenius at 7 must have exactly 2 fixed points on the roots, and there are 2 elements of the Galois group that have that property, and they form a conjugacy class. So the conjugacy class of Frobenius at 7, we've just calculated to be this pair of elements of the dihedral group of order 8. And this is a general phenomenon. You can very quickly calculate what the Frobenius element P in a given Galois group is. And Chebotarev's theorem says that if I choose a conjugacy class in a group, Galois group of some polynomial f, the fraction of primes p for which Frobenius at p is equal to that conjugacy class is exactly proportional to the size of the conjugacy class. So, for instance, very rarely is Frobenius 1, only 1 over the order of the Galois group times this Frobenius become 1, which is the same as saying that the polynomial splits completely over Fp. And this immediately implies Frobenius' theorem in retrospect, just to retry, what I've told you is immediate consequence of this. And I wanted to mention that there's a special case of this. If I apply this to the polynomial, another application of Chebotarev's theorem, if I apply it to the polynomial x to the n minus 1, the Galois group in this case is just the multiplicative group of numbers co-prime to n modulo n. Frobenius at p turns out to just be p modulo n. So Chebotarev's theorem tells you that there's infinitely many primes in any congruent to a given, if I have an integer a co-prime to n, then there are infinitely many primes congruent to a modulo n, which is Dirichlet's famous theorem on the and primes in arithmetic progressions. Okay, well, I've said a lot about equations of one variable, but is this a more general phenomenon? Well, let's look at a simple equation in 2 variables. The sort of simplest non-trivial case of this is to look at a cubic equation in 2 variables, which, at least if you choose a rational point, if there is a rational point, can always be put in this form: a quadratic in y equals a cubic in x. These are the so-called elliptic curves. Another way of thinking that that's the same as a curve of genus 1, a curve whose complex points look like a torus. That may look a very special form for the equation. It is in fact the general curve of genus 1. And let me, for simplicity, assume it. So here C and D are to be thought of as chosen constants, and X and Y are going to be allowed to vary. And I want the thing to be smooth. Otherwise, in fact, the study of it is easier, which is just some inequality on C and D. Mustn't make a bad choice. And then I'm going to consider the number np, which will be the number of pairs x and y modulo p that satisfy the congruence y squared congruent to x cubed plus cx plus d modulo p. And again, we want to ask how that varies when the prime number p varies, but fixing c and d. So let me start with an example. It's not quite in the form that I wrote on the previous page, but it's a quadratic in y equals a cubic in x. Just slightly simpler to write it in. I could put it in the form on the previous page, but make the equation look more complicated. And let's start. I've here written a table just counting the number of solutions modulo various prime numbers p, 2, 3, 5, and so on. And the first thing you observe is that, unlike the case of equation with one variable where the number of solutions stays bounded, here the number of solutions is bounded. And in fact, it grows roughly with p. So it's of the same order of magnitude as p. So it's simpler not to tabulate the number of solutions, but the difference between the number of solutions and p. So I've done that here. So modulo 2, 2 minus n2 is minus 2. So n2 is 4. And modulo 19, 19 minus n19 is 0. So there are exactly 19 solutions to this equation, modulo 19. Okay, let me produce another series of numbers. Let me take the formal infinite product in an indeterminate q, which I've written here, 1 minus q all squared, q times 1 minus q all squared, 1 minus q to the 11 all squared, and then 1 minus q squared all squared, times 1 minus q to the 22 all squared, and then 1 minus q cubed, and 1 minus q to the 33 all squared. And keep going like this forever. So if you're looking at any particular, if you try and multiply this out into a power series in Q and look at any particular coefficient like Q to the 10, you only need to consider a finite number of terms in this product, so you can multiply it out to any given degree of precision that you want. It's quite a pain to do, but I calculated the first 20 terms. Here they are. And there's a miraculous correspondence with the numbers that we had up here. If I look at the coefficient of q squared, it's minus 2, which was exactly the error in the point count modulo 2. If I look at the coefficient of q to the 11, it's 1. And again, the error in the point count modulo 11 is 1. And there's no q to the 19 here. Coefficient is 0. That was exactly the error in the point count modulo 19. So I'm producing, at least apparently, exactly the same series of numbers from multiplying out this thing as I did by counting solutions to this. Although these things have apparently nothing to do with each other. And this is indeed true. It was proved by Eichler in 1954 that for any prime p, this difference p minus np would be the coefficient, the error in the point count modulo p, the difference between the point count and p, would be the coefficient of q to the p in this infinite product. And in my mind, this was really a transformative piece of work. It's the first real example of a reciprocity law for equations in more than one variable. And it's the first real example of what people call a non-abelian reciprocity law, where the Galois group governing what's going on is a non-abelian group. And very quickly, following on from Eichler's work, there were a whole series of enormous generalizations of this, which I'll come to in a minute. But this was, to my mind, the transformative event in the subject. Well, as I say, very quickly, the next year, Taniyama was already proposing in a rather vague form that what happened in Eichler's example should happen for any elliptic curve in one variable. A few years later, Shimura made it much more precise, and then Vey, a decade later, was even more precise. Although apparently in the beginning he didn't believe Taniyama and Shimura. So it says that given any cubic equation in two variables, there should be an algorithm somewhat similar to the one I described a minute ago for Eichler's example that will give you the difference between p and the number of solutions to this equation modulo p for any prime p by virtue of some completely different sort of calculation. So this was finally proved in beginning of this century, 2001, following ideas that were introduced in the 1990s by Andrew Wiles. I should say that, so I said somewhat similar effective algorithm. This fact that I was multiplying out a huge infinite product is really rather special. I chose that example partly because it was the first example and partly because it's easy to explain. It is a special case of the general algorithm, but it's maybe not obviously so. The general algorithm is an algorithm that involves finite index subgroups of the group of 2 by 2 invertible matrices with integer entries, SL2Z. This discrete group acts, for instance, on the hyperbolic plane. And you can think of the algorithm either involving the group theory of the finite index subgroups of SL2Z, or maybe the topology of the two manifolds, which are the quotient of the hyperbolic plane by this discrete action of this group. And I'm afraid I don't have time to go into exactly what this algorithm is. It is very effective. It is the big infinite product I wrote down, in fact, can be used to define a function on the hyperbolic plane, which is nearly invariant under the action of a certain subgroup of index 12 in SL2Z, which is where the connection comes from. Well, when one knows one of these reciprocity laws, one gets many consequences. One consequence I wanted to mention is applications to L functions and zeta functions. Given an elliptic curve over the rational numbers, or any other variety over the rational numbers, one can define so-called zeta function, which is maybe most simply defined. You choose an integral model. You take a product over all closed points. I'm not going to be, those of you who don't know this, it doesn't matter, I'll be moving on to something else in a minute. You take the product of over all closed points of this, so an infinite product of this simple function of a complex variable S, which I've written here. This is the order of the residue field at that point. This will converge in some right half plane. You may have to fudge it at a finite number of factors where the model you chose has some sort of bad reduction. But the general conjecture is that this should have meromorphic continuation to the whole complex plane, should satisfy some functional equation between S and, in this case, 2 minus S. And its special values are believed to control arithmetic properties of the elliptic curve, be related. The famous Bertrand and Dyer conjecture relates special values of this zeta function to the number of rational solutions to the original equation, number of solutions in the original equation with rational x and y. There's a sort of formal similarity to the Riemann zeta function. If I replace E by spec Z, then the closed points are exactly the prime numbers, and I would just get the product of 1 minus 1 over P to the S to the minus 1 over all primes P. That would, and you'll be able to obtain the Riemann zeta function. The only way I know of proving analytic properties of these zeta functions that arise in number theory and geometry is via a reciprocity law. Okay, so how would one prove the Shimura-Taniyama? How does one prove the Shimura-Taniyama conjecture? And I'm not going to say very little about this, but again, it's a Galois theoretic based proof. We no longer, before we had this finite number of roots which were permuted by the Galois group. I can't quite talk about that anymore when I've got this equation with more than one variable. So how does Galois theory enter the picture? Well, the first thing to do is to package the Galois groups of all one variable polynomials together in one large group. If one polynomial divides another, then anything that permutes the roots of G, preserving the rational polynomial relations between them, will also permute the roots of F, so I get a surjection from the Galois group of G to the Galois group of F, and I can package this all together by taking the limit over all one-variable polynomials of the Galois groups. And I get a large infinite group, which is called the absolute Galois group of Q, which is somehow recording the information about the roots of all one-variable polynomials. Has a natural topology, being an inverse limit of finite groups. Right, it's what's called a profinite group. And just as we saw there were special elements in the Galois group of any polynomial, individual polynomial, those special elements, the Frobenius elements indexed by the prime numbers, fix together when I take this inverse limit, and this group is somehow populated by these Frobenius elements. You have to be a bit careful that exactly what's true is slightly technical to state, because for any given polynomial, there are a finite many of primes that don't have a Frobenius element for that polynomial. And when you take this inverse limit, that sort of number piles up. But nonetheless, in some way, you can still talk about Frobenius elements somehow in inverted commas, this group GQ. Okay, so what have they got to do with this elliptic curve? E is this nice symbol for this cubic equation in two variables. Well, one of the basic ways of studying varieties is to look at their cohomology. In the case of an elliptic curve, if you look at the complex solutions using the Weierstrass P function, you see that it looks like a torus. And so its H1 is rank 2. You have the spanned by the two different loops around the torus in two different directions. But if one simply takes the cohomology with say rational or integer coefficients, that doesn't seem to carry any arithmetic information. But if I replace the coefficients with the L-adic numbers, so if I select an auxiliary prime L, then I can form the L-adic numbers. One way of thinking of it is completing the rational numbers with respect to a distance where two integers are very close, L-adically, if their difference is divisible by a large power of L. Alternatively, I can take the inverse limit of z mod L to the RZ as R goes to infinity, and then invert L. Anyway, these are somehow, just as the real numbers are completions of the rational numbers, these are, from an arithmetic point of view, equally good completions of the rational numbers. Anyway, there's some large topological field. If I take the cohomology not with rational and integer coefficients, but with L-adic coefficients, as I say, for any auxiliary choice of prime L, then it turns out that this group does have an action of the Galois group. A linear action, it turns out. So we get a representation from the Galois group of Q to 2 by 2 matrices over the L-adic numbers for any auxiliary prime L. So here's the written two-dimensional representation of the Galois group of Q. And this representation is going to somehow replace the action of the Galois group of a polynomial in one variable on the roots of that polynomial. Now we're going to get a linear representation. Of course, you can turn a permutation representation on the roots into a linear representation by just taking the vector space spanned by with the basis consisting of those roots. So I say we get for each L, we had to choose this auxiliary prime L. We've got this infinite series now of representations of the Galois group. The natural question is, how far does it depend on L? And the first answer to that question is it depends enormously on L. For different primes L, these representations look very different. The images are very different groups. But at special elements, the Frobenius elements that we mentioned in the Galois group, these representations come together. The image of the Frobenius element does not depend on L. And more than that, the image of the Frobenius element, which is now a 2 by 2 L-adic matrix, but it's somehow really a 2 by 2 rational matrix because it didn't depend on L, it sits in any situation. Its trace is just P minus NP, the difference between the number of points on this elliptic curve modulo P and P. And these were the numbers we were wanting to study when we were trying to prove a reciprocity law about the elliptic curve. And the way we've managed to have success in studying this problem is not studying the solutions directly, but by studying representations of the Galois group, studying these representations REL. And while I'm talking about these elliptic curves, I want to mention that these this is an example of what's called a compatible system of L-adic representations, which arises repeatedly in the theory. Instead of, when you have a geometric object, you're having one representation of a Galois group, you have a whole series indexed by the prime numbers L, and they look very different except at these special elements, the Frobenius elements, where this system of representations comes together. Okay, well, that's all I'm going to say for now, at least, about the proof of the reciprocity law for elliptic curves, that it somehow uses Galois theory. I want to go on to more complicated equations and systems of equations. So Langlands in the mid-70s proposed a similar reciprocity law that applied not only to one variable equations or cubic equations in two variables, but applied to any system of polynomial equations in any number of variables. And whereas we saw in the example of elliptic curves, the finite index subgroups of GL2Z coming in Langland's general reciprocity law, finite index subgroups of GLNZ come into the somehow what are going to provide the algorithms for counting the number of solutions. So as I mentioned before, this is still mostly unknown, even for equations of one variable of degree 5 or more, we don't know. And just as in the case of elliptic curves, if you know a reciprocity law, you get meromorphic continuation of the corresponding zeta function and its functional equation. Well, so how might one attack these general reciprocity laws? Again, the only technique we know at the moment is via Galois theory. And what I described in the case of elliptic curves was generalized to all varieties, or at least maybe say all smooth projective varieties, by Grothendieck in the 1960s. So if I have any smooth projective variety, then I can form its L-adic cohomology. This has an action of the Galois group of Q acting on it linearly. This is for any auxiliary prime L. If X has good reduction at a prime P, it remains smooth. Then Frobenius at P makes sense in this representation. And if I can express the number of points on X modulo P, namely the number of solutions to the equations defining X when I do arithmetic modulo P, in terms of the matrix which is Frobenius at P on this, or on these cohomology groups, strictly speaking, I need not one, I need all the cohomology groups in all degrees. And again, it's now known that they have the same sort of properties that we saw for elliptic curves. If I fix the eye, Deligne showed in his consequence of his very famous Riemann hypothesis theorem in 1974 that if I let L vary, I do get a compatible system of L-adic representations. The image of Frobenius at P in the automorphisms of this QL vector space does not depend on L. As I say, by Grothendieck's theorem, this Galois representation, this representation of the Galois group, we have this compatible system. By Grothendieck's theorem, it's telling us about the number of solutions to the equations defining X if I reduce modulo P, but it also tells us not only about what goes on when I work modulo P, it also tells us about what turns out what goes on if I work over the complex numbers, if I look at the analytic theory, complex analytic theory of this variety X, if I look at its solutions over the complex numbers, one can do Hodge theory. That splits up the cohomology into certain Hodge subspaces, Hij of X, sort of fundamental to the analysis of X as a complex variety. And it turns out that this Galois representation, this vector space as a representation of the Galois group, is including information about what's going on in the complex world over the complex numbers if one does a complex analysis of this space. And in fact, it encodes these Hodge numbers. So it also has a special property. It's not a random representation. It's what we call a de Rham L-adic representation. I don't have time to define that, but in fact, it just just concerns how it behaves when I restrict to a rather small subgroup of the Galois group. But it's the property you need to be able to predict numbers which turn out to be the Hodge numbers over C. So that something like this was true was conjectured by Tate in 1967, wasn't proved until about 1990. A whole series of mathematicians, which I don't have time to list them all, worked on this problem, and there are now several proofs. Well, so we saw that the Galois representations that arise from systems of equations have these two special properties. The Frobenius at P makes sense, at least for all but finitely many primes P, and the representation is de Rham, which is this property that allows one to predict the Hodge numbers. So we'll define an L-adic representation of the Galois group of Q to be algebraic if it has these two properties that the ones coming from geometry have. And what's believed is that this really does single out exactly the representations that arise in geometry. I've just told you that any representation from the L-adic cohomology variety has those, is algebraic, and Fontaine and Mazur have conjectured that if you have an irreducible algebraic representation, it does occur in the L-adic cohomology of some smooth projective variety. So we believe we know a purely algebraic characterization of those Galois representations that come from geometry. And it's also believed that somehow they really completely control the geometry. We've seen that they control the point counts when one works modulo of prime P. We've seen that it controls the Hodge theory over the complex numbers. But more than that, one somehow believes if the same L-adic representation occurs in the cohomology of two smooth projective varieties, there's a geometric reason for it. Technically, there's a correspondence on the product of the two varieties explaining it. It's the celebrated Tate conjecture. So in some way, we believe that studying these algebraic L-adic representations this is what Jim Arthur was talking, sort of what he was talking about when he talked about motifs. Motifs is another way of talking about the part of the smooth projective variety that corresponds to a given irreducible L-adic representation. Anyway, given these two conjectures, we believe that studying smooth projective varieties and their parts is somehow the same as studying L-adic representations. Well, to state a reciprocity law, one needs not only the sort of arithmetic side, the side involving either varieties or polynomial equations or representations of Galois groups. One needs the other side that's going to involve the law for predicting the point counts and so on. And I don't have time to explain that. But again, the objects are going to be cuspidal automorphic representations, which is some analytic object connected to finite index subgroups of n by n integer matrices with determinant plus or minus 1. And one has to single out a certain subclass of them, which we call algebraic, which involves the properties of the eigenvalues of certain differential operators acting on these, as I say, analytic objects. One can also think of them, good way, a sort of more geometric way to think of them is maybe as cohomology classes of quotients of some symmetric space, the space of n by n positive definite real symmetric matrices under the congruence action of GLNZ. Gamma sends G to gamma G transpose gamma. One can take GLNZ acts discretely on this set of positive definite symmetric matrices. One can take a quotient and look at the cohomology of quotient. The quotient, I should point out, is usually a odd dimensional real manifold, so there's no algebraic geometry going on. And then the general reciprocity law is that there should be some natural bijection between irreducible n-dimensional algebraic L-adic representations, which we believe is roughly the same thing as the motif, and on the other hand, algebraic cuspidal automorphic representations of GLN. As I say, something like this was proposed by Langlands in the mid-70s, make precise exactly what automorphic representations were involved was done by Clausel in the 80s, and then one wants to make, about a few years later, one wanted to make precise which Galois representations to consider, and that was proposed by Fontaine and Mazer. Should be natural. Well, I don't really have time to say what that is, but in particular, if I have an L-adic representation, I want to know what the images of the Frobenius elements are in terms of the automorphic representation. We should at least be predicting these. And this again would have applications, for instance, to zeta functions of variety. Okay, well, what do we know? Presented the conjectural picture. Well, there are two directions. We might want to start with the automorphic object, something to do with subgroups of GLN of Z, and try and go towards Galois representations and motifs. Or one might want to go back in the other direction. Going back in the other direction is really the reciprocity law, but it seems to be hard to go back if one can't at least go in what's supposed to be the easy direction. And we now know that if we start with a regular algebraic cuspidal automorphic representation, we can associate it to a system of L-adic representations with the desired properties, and in many cases we're going to associate to it a motif. That's the language you like to speak in. So regular is I can talk about regular on. So for those who know what means, you could use the word cohomological, maybe equivalent to the maybe more familiar word cohomological for the experts. For the non-experts, I will define it in a minute on the Galois side and then leave you to imagine what it might be on this side. In some definite sense, most algebraic cuspidal automorphisms seem to be regular. At least if you stick to self-dual ones, where most study has been made, then in a definite sense, most are regular. So from the automorphic side, this condition doesn't seem to be nice to remove it, but doesn't seem too serious. So I'll explain in a minute. If one looks on the Galois side, or the algebraic geometry side, it seems to be a very serious restriction, which is rather peculiar. You have these two sets that are supposed to be in bijection, and on one side regularity seems to be the common event, on the other side it seems to be a very rare event. No logical contradiction, but it seems strange. The proof of this theorem depends on the Gauss fundamental lemma. Particularly it's used for the particular case which was actually treated earlier by Le Mans and ago, I think, is the fundamental lemma for endoscopy of unitary groups. And an enormous number of people have contributed to the proof of this theorem, which was done over a period of about 60 years, starting with Eichler's theorem in 54, and still progressing until very recently. Okay, well now what about the true reciprocity law? The reciprocity law wants to go back in the other direction. If I have one of these systems of L-adic representations, a Galois representation for each L coming together at the Frobenius elements, can I find a reciprocity law for it? And we can under two conditions, that it's what we call polarizable, self-dual, and regular. And I promised I would tell you at least what regular meant on the Galois theory or the algebraic geometry side. it means if I had a motif or even a variety, it means each of the Hodge spaces, Hij, has dimension at most 1. So if people know some algebraic geometry, they'll know that this quite hard to find things satisfying this condition. Most of the varieties you see commonly don't satisfy this condition, that if we believe this dictionary, in some sense, most varieties should satisfy, or at least most motifs should satisfy this condition. And under these two hypotheses, then it's now known that the reciprocity law holds. So, for instance, one can apply it to the L-adic representations coming from a variety, and we find the fact that if we have a smooth projective variety, some dimension d, over the Asher numbers, just a set of polynomial equations defining something that's smooth, satisfying this regularity condition that the Hodge numbers are all less than or equal to 1, then the variety X, then we know a reciprocity law. We know a different algorithm for counting the number of solutions to those polynomial equations modulo a variable prime number p, and we get meromorphic continuation and functional equation for the zeta function. And it's actually, as I say, I know very few varieties that satisfy this, so I'm not sure how generally this applies. On the other hand, it's really a theorem for motifs, not for varieties. If I take a pure motif, which is regular in the same sense and self-dual, then again you get a reciprocity law. And in this case, there are a lot of examples you can write down. So just a few examples. One that's been studied a lot is the Dwork hypersurface in projective n space, given by this equation. A is a constant and x varying. It was studied a lot, first of all, by number theorists, starting with Bernard Dwork, and more recently being studied by mirror symmetry people a lot. There's a lot of symmetries in this equation, so you can break up its cohomology or break it up into motifs, and then good proportion of the motifs that you find do satisfy this regularity condition. It also applies to the symmetric powers of an elliptic curve. So technically speaking, symmetric powers of H1 of an elliptic curve. So now not only do we have a reciprocity law for an elliptic curve, but for all its symmetric powers. And that turns out to be exactly what's required. We talked a bit about density theorems. The density theorem for an elliptic curve, just as Frobenius and Chebotarev deduced density theorems from the reciprocity law from Gauss's reciprocity law, turns out that to get a density theorem for an elliptic curve, you need not only the reciprocity law for the elliptic curve, the Shimura-Taniyama conjecture, but you need a reciprocity law for all its symmetric powers. That is guaranteed by the theorem I just gave you, so you get the corresponding density theorem for the elliptic curve. This time it's not talking about the distribution of the number of solutions mod p, which we know just goes to infinity. Instead, we have to take off the leading term, normalize the resulting error, then you get something in a fixed range, and the so-called Sartre-Tate conjecture says that it's distributed basically like this error term, normalized error term is distributed like a semicircle. Again, this theorem in this generality very much depends on the Lemon-Nagot fundamental lemma. And I wanted to finish by just saying a word about what's involved in the proof of these multidimensional reciprocity laws. The more I think about it, there seem to be two basic deep ingredients. And then you play a series of games with these two ingredients, which can get quite involved. But there seem to be two deep ingredients of a very different nature. The first is the Langland's Arthur Clozel theory of cyclic base change for GLN. If I have a Galois representation of a Galois group, I can restrict it to a subgroup of finite index. In fact, I can even restrict it to a normal subgroup with cyclic quotient, or cyclic quotient of L power. A very simple operation on Galois representations. If I believe there's this dictionary between Galois representations and automorphic forms, I have to be able to do the same with automorphic forms. On the side of automorphic forms, it's far from obvious what this corresponds to, this very simple operation on Galois representation. And this is somehow the strength of these reciprocity conjectures. Things that are very simple in algebraic geometry become very hard in analysis, and things that are easy in analysis become very hard in algebraic geometry. Nonetheless, without proving the reciprocity law, Langlands and Arthur and Clauzel were able to prove this particular example of what they call functoriality, this particular operation on automorphic forms, which should mirror something very simple on the Galois side, or the algebraic geometry side. And it's the use of this, and this particular example of what would be a consequence of reciprocity is in fact extremely useful in the proof of reciprocity. So that's one key ingredient, and what goes into this is sort of analytic. It's an analysis of the Arthur Selberg trace formula. The other key ingredient of what's called automorphic lifting theorems, which are of a very different nature, an algebraic nature, come from the study of things like Galois cohomology. And the base, although the actual conditions are somewhat complicated, the basic form of these things is that if I have two of these L-adic representations, which when I reduce mod L, that are close somehow, when I reduce mod L, they look the same. If one of them satisfies the reciprocity law, is automorphic, then so is the other one. And as I say, by taking these two ingredients, playing them off against each other, one can get quite a long way. And again, this step also, in fact, relies on the Le Monde-Legault fundamental lemma, because at the moment we don't know how to do this on GLM. We have to do this on a unitary group, and we have to do what's called the transfer or base change of the automorphic representations between the unitary group and GLM, which relies on, again, on the trace formula and the fundamental lemma. Let me finish by saying what, to my mind, in all these theorems, there was this regularity hypothesis, and to my mind, the really big question in the subject is how to get rid of regularity. There are some small number of non-regular cases that people have been able to handle, but the general non-regular case, as far as I know, nobody's got any idea of how to approach it. So, for instance, if somebody could prove a reciprocity law for abelian threefolds, I don't know any way of getting my hands on arithmetic properties of the automorphic representations of SO7 that should correspond to them. It's this regularity hypothesis, which I think is really the barrier, maybe to proving the general. Okay, I'll stop there.
Any questions?
What does the abelian threefold have to do with SO7?
Well, the cohomology H1 of an abelian threefold is a six-dimensional space with a symplectic pairing. So the Galois representations go into GSP3, and the Langlands dual group is SO7.
In the slide where you described the result on going from automorphic homological representations to Galois representations, you had the word algebraic at the beginning and also at the end. Did you just slip that in, or that?
Sorry, which slide was it, Michael?
The latest results on homological, on Galois representations. That's the homological automorphic representation.
I've gone too far. A Galois representation.
Yeah, before that.
There we go.
Yeah, so algebraic analytic representation. I'm asking about the Jerome condition.
Oh, yeah, you're right. So the sort of fully complete, yeah, you're right, Mike. The fully complete version of this theorem with all the local conditions, compatibilities one wants, is known in the self-dual case. So I guess I originally wrote this theorem in the self-dual case and put algebraic. The generalization to the non-self-dual case is very recent, but it's not yet written. And I shouldn't be claiming that in the non-self-dual case we know algebraicity of the analytic representations, though maybe that's not impossible that one will know that. But I didn't mean to claiming algebraicity in the non-self-dual case.
Any other questions? Let's thank Richard for such a wonderful question.